Okay, what we want to do now is we're going to run you through the simulation software. I come across this little tool and it's quite amazing actually. Now this is going to show us how valence shell electron pair repulsion works, or how bonding works in general. I'll just move around so the lights come back on again. Alright, so what we're going to do is, this is basically our starting atom, and what we can do is we can add to the starting atom one other atom. You're not going to move this thing around, and what you'll find is that it's pretty straightforward, I think, that if you've only got two atoms and one bond, and if I ask you what the geometry is, you would probably say linear, which is quite amazing. It is, it's in a line. And if I ask you what the bond angle is, okay, it doesn't even show one here because there isn't any, but it would be 360 degrees, okay, would be the bond angle if it were able to show that. So that's an atom in the middle with one bonding set of electrons, and here's our bonding set of electrons here. What I'm going to do now is I'm going to add a second set in, and what you'll notice is that the actual middle atom, okay, moves along with the two outside atoms, but this is a section of bonding electrons here, and this is a section of bonding electrons in here. No matter how hard I try to try and make this into a V shape, if I've only got two sets of electrons around the central atom, what you'll find is, if I show the bond angle, funny enough, it's going to be 180 degrees. No matter which way I try and force this, this molecule, it's always going to flick back, you'll notice, to 180 degrees, because that's the greatest distance that this negative charge and this negative charge can appear in the structure. And of course this would also be, funny enough, linear. Okay, now we introduce a third set of electrons. So now we've only got 1, 2, 3. We've got 3 bonds, 3 sets of electrons. And no matter how hard I force this, you'll see that it's going to eventually go to, and if I show the bond angle for this one, and if I try and move that, or if I try and move that atom closer to that one, it doesn't let me do it. This is always going to be 120 degrees because that's the furthest apart. We've got this set of electrons here, this set, and this set. So we've got 3 sets of electrons here. The geometry would be called trigonal planar, is what we actually call it, essentially. And if we look at the angles, as I just said, it's 120 degrees. So trigonal planar, and if I move the molecule like that, you can see it's in an exact flat plane. That's why it's called trigonal. 1, 2, 3, trigonal planar in a triangle. All right, what about if I put 4 sets in? Let me turn the geometry off and turn the bond angles off. If I put 4 sets in, now this is getting towards like a methane molecule. So if I try and move, let me see if I can move, I can't. So no matter which way I move the structure, you'll notice that all of these other electrons, 1, 2, 3, 4 sets now, they all are going to repel one another, and that's how valence shell electron pair repulsion works. And this is, we're seeing it like real time. So, and this is the great thing about this model. So if I try and move it closer, it's just going to keep on repelling. The bond angle, well, what you'll notice is the bond angle for all these is going to be the same. If I try and move that one close, no, it won't let me do it. If I try and move this one, no, won't let me do it. So it's going to maintain that bond angle all the time, and we call that tetrahedral. That shape is basically a tetrahedral shape, as you can see. All right, now, what we'll do is we'll do the same thing, but I'll show you how it works with multiple bonds. So I'm going to get rid of all the single bonds, get rid of that one, that one, that one. Doesn't really matter. So if I've got that and that, I've still got the same idea. Even though I've got 2 double bonds, we've still got one group of electrons here and one group of electrons here. So it's the same as what we had with the single electrons or single bond before. So if I can keep on twisting that, valence shell electron pair repulsion says the bond angle will be, have a guess, 180, good, and the geometry will be linear, excellent, all right? So it doesn't matter how far we do that, it's going to keep on twisting, okay, to that. Now I can add another double bond, and you can see down the bottom, trigonal planar, and the bond angle's 120. It doesn't matter how I move it. So we've got 1, 2, 3 sets of electrons around that central atom. If we had 4 of them, if it did exist, you'll notice that it's the same. I just happen to have 4 double bonds if this molecule existed. And again, same structure, tetrahedral, because it's based on 4 around the central atom. Just going to drag those away, take those away. Oh, that's the take it away one. And you can see we've also got other structures that we'll look at a little bit later. So that's really just how the structure actually works in terms of valence shells. So these are the valence shells, and depending on how many we have, that determines the shape and the bond angle of the molecule. And that's our introductory stuff.